In part 1 of question 5, to show that this quadratic is positive for all values of y, we need to get the variable y within a squared bracket. So if we simply complete the square on this, so we can say y squared minus 4y plus 7 is equal to, or identical to, y minus 2 all squared. Take away the 4, so this first bit gives us y squared minus 4y, and then add back the 7. Simplify that, that equals y minus 2 squared plus 3. Then we need a statement that says y minus 2 squared is always greater than or equal to 0 for all y. Therefore, y minus 2 squared plus 3, if I add something to that, is always going to be greater than 0 for all y belong to R. In fact, it will be greater than or equal to 3, but the top statement there is what we've been asked to show. You'll get no marks for this question by simply plugging in some values of y and showing that it is positive for the few values that you have chosen, or any kind of statement that discusses y squared being positive and then minus 4y being smaller than y squared, or anything like that. Just forget that, you need to complete the square. In this next bit, always, sometimes, or never true. First of all, I would be considering trying to decide for yourself which one of those you think it is. I'd be looking at considering values and what the graph looks like. So for e to the 2x, looks like that goes through 1. For e to the 3x, when x is positive, that's going to increase at a faster rate, and when it's negative, that will decrease there at a faster rate. So this is what the graphs look like. If you don't know that, then you could just also take a few values of x to try. They change depending upon whether x is negative or positive. So actually it is sometimes true. So here, consider, let's say, when x equals 1, and then you can just evaluate e to the 3 and e to the 2. And we have these values. So we have a situation here where we've shown a particular case where e to the 3x is greater than or equal to e squared. So it's true for that case. And then we want to consider another case where it is not true. So let's look at x is negative 1 and evaluate those. And we get these values, and so we can say that that is not true for x is negative 1. It is true for x is 1. So we've found one of each case. Therefore, to answer the question, Bobby's claim is sometimes true. And in fact, it is true for all x greater than or equal to 0, and it is false for all x less than 0. That's more than you need. For a sometimes true argument, you just need a particular case where it is not true and a particular case where it is true. For this one, we are specifically asked to use proof by contradiction. So the first thing we do is we assume the negation of the statement, and in this case it would be there exists n such that n squared is even and n is odd. So we're assuming n squared is even, and my assumption is that there exists an n, not that it must be even, but there exists an n that is odd. Now, the fact that we are even talking about even or odd numbers means we must be talking about integers. We do not use the words even and odd to describe fractions or decimals. It must be n belonging to integers, and moreover here we're told that we're looking for positive integers. Okay, so that's our first assumption. Now, so n is odd. We're going to use the trick, let n equal 2k plus 1, where k is an integer. And since we want n to be positive integers, we could specify that k is a positive integer as well. N squared then, and just a simple bit of algebra, is 2k plus 1 squared. That gives us 4k squared plus 4k plus 1. And I want to show that this, I can look at that and see that it's odd. I want to demonstrate that it is in fact odd there. So I would write 2 times something. Obviously I could factorize this further, but I'm really trying to demonstrate that this is a multiple of 2 plus 1. Therefore, n squared is odd. This is a contradiction. Contradicts the assumption. Therefore, my assumption is not true. If n squared is even, then n must be even. This last one is a bit annoying in a way, in that you need a bit of practice at this. I've done a separate video with lots of different practice at these always, sometimes, or never questions. When you see it and you know it, it's not too bad. But let's have a look. Consider the two numbers. Let's say pi. There is an irrational number, and let's say the number 9 minus pi. These are two different irrational numbers, and if I add them together, so the sum here is pi plus 9 minus pi, and we can see my irrational parts cancel out, and I get 9, which is rational. So there I've got a case where it is not true. So not true that the sum of my two irrational numbers is irrational. And then I want to show a case where it is true. So let's consider another pair of irrational numbers. Let's say root 2 and root 3. And here I could sum those. Root 2 plus root 3 is irrational. Just state that that is irrational for 2 marks, and that is true. So therefore, Ying's claim is sometimes true. Just have a look at the mark schemes. I've got a comment on the mark scheme for this one. And then please do watch the other video that I'm making on extra practice at this. So here's my mark scheme for the first two. You can pause that and have a look if you need to. Mark scheme for the second one. Sorry, just pop back to that mark scheme. Oh, it won't let me. Okay. So in this one, note that the first method mark here is for when it's a sometimes true, but it's where it fails, where it is not true, is for our method mark. And then the second mark for completeness is where it is true. Okay. And in previous papers, examiners have been quite clear on this, that when it is sometimes true, you must first look for where it is not, and then go to where it is true. Okay, if you put, as long as you put both sides down, both examples, one where it is true, one where it is not true, you get full marks. If you just put one side down, potentially you don't get any marks. But if the side down that you put is not true, you would still pick up that method mark. It's a bit strange. Okay, please go to the other video to have a look at that.